Welcome everybody to this class. This is lecture 5 on chemical kinetics. We will start from where we had left off in the previous class, and if you would remember that in the previous class we had introduced a concept referred to as the degree of advancement of a reaction, and we were monitoring d xi. So, that was xi is the degree of advancement of the reaction over time, that is dt. So, at the end of the class, nearing the end of the class, this is where we had left off. What we had started to do, this was the reaction we were looking at, acetaldehyde going to methane and carbon monoxide. Then we said we assume ideal gas behavior. Assuming ideal gas behavior, we write the initial number of moles. We say that this is the progress of the reaction being denoted by the extent of the reaction, which is psi, or the degree of advancement of the reaction. Once we are done with that, we started writing down the number of moles of each and every species. So, this was the number of moles of acetaldehyde N0 CH3CHO or N0 CH3CHO minus xi. Why it is minus? Because we are losing the reaction or reactant. Then NCH4 is equal to xi. Why? Again, this one is equal to xi. Number 1, N0 CH4, there was no product to start with, CH4 was not there, and then because it is a product, you are gaining it as a function of time, it is having a positive value and the coefficient is 1. So, it is NCH4 is equal to xi, and same we are having NCO, which is also equal to xi. Then what we have is initial number of moles, the initial number of moles is N0 CH3 CHO is equal to N0. So, that is what it is, right, where 0 or naught represents the initial number of moles, and N0 CH3 CHO essentially is what? N0 CH3 CHO means that this is the only species that I have present at the start of the reaction. Now, then how can I write the total pressure? So, the total pressure can be written as follows. So, the total pressure is equal to, so this is equal to the pressure from CH3 CHO, the pressure being exerted by methane and the pressure being exerted by carbon monoxide. Now, again remember that we are taking the ideal gas assumption, where ideal gas means P times V is equal to N RT, where N is the number of moles. So, having done this, what I can do is I can write P CH3 CHO is equal to the number of moles of acetaldehyde, which is N0 minus xi, right, into RT by V. Why? So, this is what we are doing. So, ideal gas PV is equal to nRT. What is N? N for acetaldehyde is N0, right. So, this is N0 minus xi, because xi is the extent by which the reaction has progressed, times RT by V. So, this is what we have, P CH3 CHO is equal to N0 minus xi times RT over V. Likewise, we can write the same for PCH4, this is equal to xi RT over V. Why? Because xi is the number of moles of methane, and then the same for carbon monoxide is xi RT over V. Okay. Now, having written this, now we can go for expression of the total pressure. So, how do I write that? Then I can write, remember the total pressure P total is equal to P CH3 CHO plus P CH4 plus P CO, right, sum of all the components present in the reaction. Then we already have expressions for each of these PCH3CHO, PCH4 and PCO, we just wrote those down. So, I can write that as N0 minus xi, this is the number of moles of acetaldehyde, plus xi, the number of moles of methane, plus xi, the number of moles of carbon monoxide, times RT over V. So, what did we do out here? We essentially just added all these up, PCH3CHO plus PCH4 plus PCO. RT by V is a constant. Why? Because temperature is a constant, volume is a constant, and hence I can take RT by V out as a common factor. So, that is what I have done. Then P is equal to N0 minus xi plus xi times RT over V. So, then I can write P is equal to N0 plus xi, then RT over V. I can further simplify this by writing N0 RT over V plus xi RT over V. Now, this is a significant point, or this is a significant step in the reaction. So, if you would realize, this component has N0 times RT over V. N0 was the initial number of moles. So, remember, so if I write it here, N0 was the initial number of moles. Okay. So, N0 was the initial number of moles. If that is so, then I can say that this one is the initial pressure, which we can say is P naught. So, the initial pressure is P naught. So, P naught is equal to N naught RT over V plus this xi RT over V. So, P now can be further written as, the P can be further written as, that is the total pressure can be further written as P is equal to P naught, which is the initial pressure, plus xi RT over V. Now, what we do is we look at it, take the differential form of it, differentiate it with respect to T. So, the total pressure, which is equal to d P naught over d of T plus d of T xi RT over V. If we do that, now P naught is a constant, right. So, I can say P naught is a constant because the initial number of moles is N naught, which is a constant. Hence, this one is equal to 0. Thus, the equation gets simplified to dP over d of T, that is the rate of change of pressure with time, is equal to RT over V. RT over V, R is a constant, T has been kept constant, V is also constant. These were the initial conditions of the reaction, d xi over d of T, right. Hence, I can further write this one as, so let me write this again on the next page. So, what we just had was dP over d of T is equal to RT by V d xi of dt or d xi over d of T, right. Hence, I can say that 1 by V d xi over d of T is equal to 1 by RT dP over d of T. So, this is what we were aiming for in the problem. So, what have we done? We have looked at the change in the extent of the reaction. So, we have looked at the change in the extent of the reaction, which is d xi over d of T. This times 1 by V, V is a constant, is equal to 1 by RT dP by dt. That means if I follow the change of pressure with respect to time, that is equivalent to following the change of the extent of the reaction as a function of time, and this 1 by V times d xi over d of T is what? Nothing but the rate of the reaction, and thus we say that the rate of the reaction can be monitored by monitoring the change of pressure with respect to time. The only thing is there are these constants 1 by RT, because these were kept as constants. So, thus this example shows you how to incorporate or how to express the rate of a reaction in terms of the change of pressure in a gaseous reaction, the example being the one we were discussing right now. So, hopefully by doing this exercise or rather an example, you would understand the essence of this xi, the degree of advancement of the reaction, and the utility of the same in expressing the rate of the reaction in terms of whatever you want it to be, whether it is a concentration or in case of gaseous reactions whether it is the pressure. So, now what we will do is, having established this concept of rate in terms of xi, having looked at operational definitions of rates of reactions in terms of the coefficients and changes, what we will now do is, we will now look at something which is much more widely used. That means, we are slowly taking a step into the crux of chemical kinetics, which is our kinetic analysis and rate equations. So, then I start this section by writing kinetic analysis of experimental data. Okay. And we will soon realize what it means, but in short the significance is that when I am doing an experiment on or related to chemical kinetics, I am following the rate of change of concentration either of reactants or products as a function of time. I generate some plots, and what we will see is what do those plots help us in interpreting in terms of the different definitions of rates which are out there. So, let us look at this one first. What we will try to discuss out here is something known as average rate, something known as average rate. So, for example, you take this one, you take this plot. Okay. So, what I have here is time, it can be any unit, let us take it seconds, does not matter. What I have on the y axis is concentration, and what I am doing is, in this case as an example, I am looking at the change in concentration of the reactant as a function of time, right. I can also do it in using products, but let us stick to change in concentration of the reactant. Okay. So, this is what happens then. I will draw a line now just to show you how it changes as a function of time. Okay. Now, there is an arbitrary reaction I am taking, a very general reaction, I am not naming the reaction as such. Okay. It can be applicable for any general reaction. Now, suppose we put our experimental points, say for example, there is a point out here, right. Let there be a point out here, let there be a point out here, and let there be a point out here. So, the line is a smooth line through some of these experimental points, right. Now, it is very similar, if I can kind of take you back to a couple of lectures ago, it is very similar to this kinetic reaction profile, that one is also kinetic reaction profile, and you can see for these blue lines which corresponded to the products, the reaction between hypochlorite and bromide, giving hypobromide and chloride, how the reactants were changing as a function of time, and this is what I am doing out here too. But what are we trying to do, or what am I trying to tell you, or what am I trying to emphasize upon? So, let this correspond to T1 let this experimental point correspond to T2, correspond to T3, correspond to T4, right. So, let this concentration correspond to C1, C2, C3 and then C4. So, what we have done is we have taken a few experimental points, we have labeled them correspond to the times T1, T2, T3, T4 and the corresponding concentrations at those times C1, C2, C3, C4. Now, when we define the average rate, say we define the average rate between C1 and C3. So, when we take the average rate is defined as, the average rate is defined like this. The average rate is equal to, say I am taking these 2 points C3 and C1 corresponding to T3 and T1. So, I write C3 minus C1 over T3 minus T1. So, that is my average rate. So, if I can write here, this is average rate, this is equal to C3 minus C1 over T3 minus T1. I am sure you now realize there is one thing that is missing. Based on our previous discussions, the rate has to be a positive quantity. C3 minus C1 is negative because C3 is less than C1. T3 minus T1 is positive because T3 is greater than T1. Hence, this expression is negative. Because this expression is negative, the rate cannot be a negative quantity. I have a negative sign out here. And again, whenever you express the rate in terms of the disappearance of a reactant, it is always preceded with a negative sign, which signifies A, it is a reactant which is disappearing with time, and 2, the rate is a positive quantity, and that is why this negative sign has to be there. But this is not so useful. In very few cases, very few cases, you would actually see the average rate being used extensively. It is not extensively used. Anyway, this one we can write as minus delta concentration over delta T. So, a delta means a finite change in concentration over T, a finite change in time, that means over the time interval T3 minus T1. So, this is the definition of your average rate, and as I said, this is not what is regularly used or is that useful. What is really useful for us is to know or is to ask, if I take any time point, on this curve, say T1, say T2, say T3, say T4, say any other time point, will I be able to get the rate at that specific time corresponding to a certain concentration, right. What does this bring us to? This brings us to the concept of instantaneous rate, and that is the one we normally use throughout. So, let us go and take a quick look at what instantaneous rate is all about. So, we are talking about instantaneous rate. Again, let us look at a similar curve, right, where the reactant concentration is decreasing as a function of time. So, let me have a curve like this. Okay. Again, same labels, this is concentration of reactant. I say the reactant is represented as R, right. This is time in this direction increasing, right, and my reaction profile or the kinetic reaction profile goes like this. Okay. And remember, what we are discussing out here is something referred to as instantaneous rate. Now, suppose these are certain time points or experimental points. Now, suppose I want to know that at this instant, that means at this instant, at this time point, what is the rate? What is the rate at this time point, say, which corresponds to, say, in this case it is T1, say. So, what would I do is I would draw a tangent, if I can draw it properly. Let me use a different color. I would draw a tangent right at this point. So, let me just change this. So, I draw a tangent right at that point. I draw a tangent, and then what I do is I take the slope of the tangent. So, that means I have drawn a tangent right at T1, right at T1. Once I have drawn the tangent right at T1, this is what the change in concentration of R, which is d of R, and along this axis I can write the change in T, which is dt. So, the way this instantaneous rate is different from the average rate is this. When I say instantaneous rate, what I am meaning is, going back to this average rate definition where it was C3 minus C1 over T3 minus T1. When I am talking about instantaneous rate, what I mean is, I am meaning that C3 minus C1 tends to 0, T3 minus T1 tends to 0. So, this is based on the expression we had out here. So, there is very small difference between C3 and C1, essentially that means I am taking the rate at a specific point. Hence, the rate or the instantaneous rate is defined as dC over d of t. So, based on this what I can write is, so based on this exercise what I can write is, then the rate, so I can write R instantaneous, which is the instantaneous rate, is equal to d of R over d of t, right, with a negative sign before that. Again, the negative sign has to be there because R being the reactant, the rate has to be a positive one. So, what is the instantaneous rate giving you, or what is the instantaneous rate all about? The instantaneous rate is the slope of the tangent, drawn at that point. That point means the point where you want to find the instantaneous rate. Okay. So, I will write it so that it becomes clear. So, then the way we characterize instantaneous rate or try to find instantaneous rate is by drawing a tangent at that instant or that time point, which in our discussion was T1. So, T1 is number 1, and then once I have drawn a proper tangent, so the tangent has to be drawn properly, right. Once I have drawn a proper tangent, then what I do is I take the slope of the tangent. So, these two things I need to do to find the instantaneous rate. Okay. So, if this is the rate, or if you are looking at the rate in terms of the reactant concentration, it would be minus d of r over d of t. If you are looking at the rate in terms of the product concentrations, it would be d of p over d of t. So, that means for products, similarly I will draw a tangent at that point, and my r instantaneous would be d of p over d of t. This time p here is product, p here is product. So, this is a very crucial difference between the instantaneous rate and the average rate. So, the average rate is taken over a longish time interval, a long change in concentration over the time interval, and it is not of that much use, that is why it is not used that often. The instantaneous rate is typically the one which is used throughout, and that is what we saw or what we looked at, how it is defined. Based on this, you can understand that I can have instantaneous rates at typically many points. So, I can have, say if you want this point now, right, if you want this point, what you do is you draw a tangent at this point, right. No, my tangent was not drawn properly, or if you want to at this point, you draw again a tangent at this point. Okay. So, if you want it here, then you draw a tangent at this point. So, wherever at that instant you want the rate, you draw the tangent at that point and then do the exercise. That means, take the slope of the tangent, for example, here you take the slope. So, from here to here, what are we looking at? We are looking at a change in the reactant concentration. From here to here, what are we looking at? We are looking at a change in time. Why? Because this is the y axis, the y axis is telling you about the concentration of the reactant, this is parallel to the x axis, it is telling you about the time that is elapsed, or rather the time interval dt, in this case infinite time interval, right, and that is the definition of the instantaneous rate, and this instantaneous is the one which is used almost all the time. Okay. There is one more aspect that we have. So, we have talked about average rate, we have talked about instantaneous rate. A very important rate that comes in, or type of rate, is referred to as initial rate, that is initial rate of reaction. Initial rate of reaction. And how do we do that? See, what does initial rate of reaction mean? Initial rate of reaction means that exactly at the start of the reaction, I need my rate. That is, the moment the reaction is started, I need to calculate the rate of the reaction. See, unless and until my reaction is started, I cannot calculate any rate. But what I am saying by initial rate is that if I have to calculate my initial rate, I have to be very, very close to the start of the reaction. I have to let the reaction start, otherwise I cannot calculate any rate anyway. But once the reaction starts, I immediately calculate my reaction rate. So, at the very initial point, at the very first few points. So, then if I have to depict it pictorially or using a kinetic reaction profile, same thing, if I have this for a reactant, this is time, this is concentration, right. If this is my initial time point, remember this is 0. So, this is my initial time point. I have to find the initial reaction rate. So, what I do is I draw, let me use this pen, this is clearer, I draw tangent at this point, I draw tangent at this point. This tangent, what does it give you? It gives you the initial reaction rate from the slope of this line. and the way this tangent is drawn is it is drawn right at the initial point of the reaction. Now, this was this was in terms of the reactant, that is why you see it decreasing as a function of time. I can do exactly the same thing in terms of the product. So, for example, if I have not done it before for the other cases, but just to complete the story, again if this is time, this is concentration of product, this is concentration of product, and I say the product reaction profile goes something like this. Okay. So, look at the initial time point now. So, the initial time point is this is time 0, and if I have to look or if I have to get the initial rate or the tangent has to be drawn right at this point, and hence again this is my initial reaction, this is my initial reaction rate from product, right. So, as usual I can get my initial reaction rate from the reactant and I can get the initial reaction rate from product. 2 points worth remembering. One, when I later what I will try to do is I will give you some idea of how people would measure rates and so on, and there is a method referred to as method of initial rates. So, method of initial rates actually takes this into consideration, right. You look at the initial rate and then you get kinetics and other informations about the reaction whichever you are doing at the time. Those things we will discuss in due course. But there are 2 important points if you are doing an experiment. So, from the experimental point of view, there are 2 key points when you do this initial rate calculation. One, it is preferred to do the initial rate calculation based on product appearance. So, that means if you are given an option, if someone asks you during calculation of the initial rate which would I rather choose, should I go and use the reactant profile or should I go and use the product kinetic reaction profile, your answer would be the product. Why? This is something we need to understand. See, when we are considering the initial rate of reaction, that is very logical, you will see. See, when you are considering the initial rate of the reaction in terms of the reactant loss or reactant disappearance, see at this point you have a huge amount of reactant, right, and then very close to that initial time point you are trying to get a measure of how much of reactant has been lost. But do realize that if you do not have a very sensitive technique or very sensitive analytical technique, because you are very close to your initial time point, right, the difference in between the 2 concentrations, that means the slope you take, the difference in between the 2 concentrations experimentally would be very small. Because this difference would be very small, if the analytical technique is not sensitive enough, then you might not get much accuracy. I repeat, when you do this initial rate calculation, so please remember this, when you do this initial rate calculation or experiment, you would rather do this in terms of the product appearance as opposed to the reactant disappearance. Why? When you consider the reactant is present, say there is no product at all, you are doing the initial rate which is very close to the starting point of the reaction, you have lost only a little bit of the reactant, say, depending upon the reaction obviously, and because there was a lot of reactant to start with and you have lost a little bit, if your technique is not sensitive enough to figure out the difference, then you will not be able to get a proper reaction rate. That means, your reaction rate calculation would not be that accurate. However, think about the product. So, that means, the rate in the reaction, if this is the initial rate, if you are very close to the starting point, which is my next point for the initial rate calculation, then the difference between the two concentrations you measure might not be high, and if the technique you are using is not a very sensitive analytical technique, then the change in concentration you get might not be the accurate one. On the other hand, think about the product appearance. See, look at this product appearance. When starting at T0, which is my initial part, even before the reaction has started, on y axis we have concentration of products, I have no product at all, right. Now, the moment my reaction has started, a little bit of product has come in, but because my initial concentration of product was 0, it becomes much easier for me to measure that change in concentration, because I am always comparing with 0 where there was nothing, and I do this change with respect to 0 or blank, that means there was no product out there, and hence I am in a much better position in terms of accurately telling or determining the product concentration and then the initial reaction rate from the product appearance. And that is why the statement was made, it is preferred to do the initial rate calculation based on product appearance experimentally. And the second point is this initial rate calculation has to be done very close to the starting point in terms of time of the reaction. It is typically, that is what people say, it is typically within 5%. So, understand what I am saying is, where would I measure the initial reaction rate, which points would I take, where would I experimentally measure? This is within 5% of the reaction, within 5% of the reaction, that means the reaction started, it goes to 100% say reaction complete, within the first 5% I would have to take my concentrations for my initial rate calculation. Finally, if you would realize from this, the slope of this line and the slope of this line, that for almost all reactions, provided they are not chain reactions, again keep this in mind, provided these are not chain reactions, apart from chain reactions I am talking about all other reactions, this initial rate, the tangent or the slope of the tangent at the initial rate is always the steepest. That means, the slope is always the maximum, that is the line is the steepest. So, we can write except chain reactions, right, the initial rate line or tangent, if you would prefer to say that, will be the one which is the steepest, that is having the maximum slope. Steepest means the one which is going to have the maximum slope, and that is why it is the initial rate. So, what did we learn from these plots? We looked at three different rate definitions. One was the average, which was delta c over delta t. Then was the instantaneous, by which we meant that you take any time point on that kinetic reaction profile. If you want to know the reaction at any time point, that is why it is called instantaneous rate at that instant, say T1, T2, T3, then what you do is you draw a tangent at that point, draw the tangent properly. Once you have drawn the tangent, you take the slope of the tangent, and that slope gives you the instantaneous reaction rate at that instant, that time point, corresponding to a certain concentration. The third one is called the initial reaction rate, and by definition the initial reaction rate corresponds to that reaction rate which is measured very close or right at the initial part of the reaction, and as I said, one of those 2 points, it is should be within the 5% of a reaction, whether it is in terms of reactants or products. And obviously, it is preferred that instead of reactant you use the reactant disappearance, you use the product appearance to define your initial reaction rate or find your initial reaction rate. This is something which is very important for you to understand and also take into consideration if you are looking at a certain experiment and trying to figure out what the initial rate is. This, as I was telling you, this method of initial reaction rates is very important in determining the rate, constant, and even the order of a reaction, which you will realize when we do a few examples later. Now, having talked about the different types of rates that are present out there, our next approach, which I will start off a little bit today, our next approach would be to figure out something known as rate expressions. That means, how is this rate related to the concentration in some way or the other. So, let us think about that for a bit. So, what we do now is we start with this concept of dependence of reaction rate on concentration, and pay attention to this. So, let me draw again a kinetic reaction profile for a reactant. Okay. So, this is again concentration of reactant, which is R. Okay. This is time as usual. Now, let me draw the profile. Suppose this is a profile. Now, let us see what is happening. Let us take a couple of points along this reaction profile. So, let us take this point out here, which say corresponds to T1, right, and I draw, I am trying to find the instantaneous rate at this point. Okay. So, if I am trying to find the instantaneous rate at this point, what I would do is I would draw a tangent at that point. Having said that, let us look at another point out here. Again, I need to find out the instantaneous rate at this time point, say, which is T2. I do that how? As before, what I will do is I will again draw a tangent. Okay. Now, hopefully you realize what I am getting at. Another time point, say I take this one T3, okay. Again I draw a tangent. I take another time point, say here corresponds to T4, and I draw another tangent. Let me write these lines as A, B, C, D, E, F, and then G, H. So, there are 4 time points. At the 4 time points, I want to know the instantaneous reaction rates. So, what have I done? At all or each of these 4 time points, I have drawn tangents. So, for time point T1, my tangent is AB. For time point T2, my tangent is CD. For time point T3, my tangent is EF. For time point T4, my tangent is GH. Now, immediately realize, because the instantaneous rate is nothing. So, instantaneous rate is what? Is the slope of the tangent, obviously with a negative sign, right, because this is a reactant we are talking about. I am not writing that, it is obvious. What you will understand is, if the slopes, if you look at the slopes of the lines A, B, C, D, E, F and G, H, this is the order of the slope. A, B, the slope of A, B is greater than the slope of C, D, which is greater than the slope of E, F, and which is greater than the slope of line G, H. So, A, B is having the maximum slope. So, this guy, line A, B, has the maximum slope, and this one has the minimum slope. I just want to mention that what I mean by the maximum slope, when I say maximum slope, what I actually mean is, it's that the magnitude of the slope is the maximum. Okay. Again, what I mean by maximum slope is the magnitude, which is I am talking about. The magnitude of the slope is the maximum. And so, please remember that whenever I refer to the slope as being the maximum slope or the minimum slope, it is always the magnitude that I am referring to. So, this is the one I am always referring to. Okay. So, this is something which is very important to keep in mind in terms of the slope or slopes that we are talking about or we are going to talk about in the later classes, right. You can see how steep this one is, less steep this one is, less steeper this one, and finally, this one is the least steep or having the smallest slope. What has happened? What has happened is, as I move from t is equal to 0 along the time points T1, T2, T3 and T4, I am losing reactant. That means, reactant is disappearing. That means, the concentration of the reactant is changing. Because of the concentration of the reactant is changing, you can see the instantaneous rate is also changing, which is defined by the slope of the tangents is also changing. So, that means, the rate is maximum at the time point T1 and it is based on the example given out, it is minimum for time point T4. The moment you see a picture like this, you start thinking this. Okay. This is why the rate of the reaction is somehow dependent upon the concentration of the reactant which is remaining. I repeat, I will stop here by this or making the statement. Since the slope is changing as a function of my time points, and since the slope is my instantaneous reaction rate, that means the rate instantaneous reaction rate is changing as a function of time. What is also changing as a function of time is your concentration, and if you try to merge both these observations, what would immediately fall out is that the rate is some way dependent on the concentration of the reactant that is remaining in the mixture, and maybe this is where all, or this is what is the starting point of the rate expression, which is proportional to the concentration of the reactant raised to some power, which we will come to know as the order of the reaction. We will look at it in more details in the next lecture. Thank you.